Unit 6. Black Holes, Whiteholes, and Wormholes. Page 42.
Are there any questions before we begin? No? This morning I'm going to introduce you to three mysterious phenomena that have been puzzling astronomers since the early 20th century. Phenomena which promise to tell us a good deal about the origins of our universe and the nature of space and time. I'm talking about black holes, white holes, and wormholes. Are you familiar with these? I'm sure most of you have heard of these things, maybe through movies, but if you're like most people, you probably really don't understand them very well, right? What I'm going to talk about today, in pretty simple terms, is what these things are and what evidence we have that they exist. Let me start then with black holes, which is probably the most familiar term for most people. The term black hole was first used back in 1969 by an American physicist named John Archibald Wheeler. He used it to describe the final stage in the life of very large stars. Black holes have incredibly strong gravitational force, so strong, in fact, that nothing can escape their gravity, not even light. And since no light can escape from them, and since we need light to see, we cannot see black holes, which is precisely why we call them black holes, right? I see a question. Yes?
If they can't see them, how do scientists know black holes exist?
Excellent question. Scientists know they exist because they can see their effect on nearby objects. For example, black holes pull gases off the surface of nearby stars. Scientists are able to see these gases being sucked into the black hole.
I see.
So, what causes black holes? Well, to answer that question, it's helpful to first consider small and medium-sized stars. In the last stage of their lives, small and medium-sized stars become what we call white dwarfs. Now, a white dwarf is a small, very hot mass which is formed when the star's gravity collapses the star. All its heat, energy, and mass are compressed into a smaller and smaller space. This makes the star hotter and gives it a stronger gravitational pull. So that's what happens with small and medium-sized stars. As I've said, though, a black hole is the final stage in the life of a very large star, and this means its gravity's much stronger. Anyone like to suggest why? Sergio?
It's larger, so it has more mass, and that makes its gravitational pull stronger.
Yes, Sergio, you're absolutely right. In the case of a large star, there's more mass and therefore the gravitational force is stronger. And as the gravitational force becomes stronger and stronger, the star gets smaller and smaller until all its energy and mass is compressed into one tiny point called the singularity. That's singularity. Got that? The singularity then sucks or pulls in everything near it, even light, because its gravitational force is so strong. So we get a black hole. In other words, the powerful gravitational force of a black hole is caused by an extremely large mass being forced into, drawn into, a tiny space, the singularity. It's a bit like taking an orange and squeezing it so hard that it becomes as small as the head of a pin, but its weight doesn't change. When a large mass is forced into a tiny space like this, we say it's very dense. So the tiny point called the singularity is an extremely dense object. Now, here's an interesting question. How small does a star need to become in order to create the huge gravitational force of a black hole? Well, just consider this. We're told that if the sun were the size of a large mountain, it would need to shrink to the size of a small butterfly. Think about that. From a mountain to a small butterfly. yet it would still weigh the same as the original mountain. It would, as we've said, be extremely dense. Now, most of their lives, stars remain a constant size because they have a balance of forces. On one side, you've got heat, which is made because the star burns fuel which helps push the star out. On the other side, there's the effect of gravity which pulls the star in. Heat versus gravity, see? So you get a balance. However, after billions of years, the star uses up all its fuel. Then there's an imbalance. There's no more heat. Gravity wins the battle, and the star collapses. Now, students often ask me what it would be like to be sucked into a black hole. The truth is, we can't really be sure. However, scientists have tried to imagine this event, and it doesn't sound very appealing. Let me explain. The area immediately surrounding a black hole is called the event horizon. Once you cross this area, the event horizon, you can't go back. The gravity there is so strong that you wouldn't be able to escape the black hole. The gravitational force pulling on your legs would be greater than the gravitational force pulling on your head, and the difference between the two forces would stretch you. Each and every atom of your body would be torn apart from the others and pulled toward the singularity at the black hole's center. There they'd be squeezed until they ceased to exist. Not very nice. Okay, enough about what getting sucked into a black hole would be like. Now I'm going to move on to different types of black holes. Basically, there are two kinds of black holes: rotating and non-rotating. Let me explain the difference. If you cross the event horizon of a non-rotating black hole, it's certain you'll die. However, some scientists believe that this might not happen if you cross the event horizon of a rotating black hole. Because the hole rotates, you may be able to somehow avoid entering the singularity, and you may even be transported to another part of the universe and forced out of a white hole, although only as millions of particles, probably. Your body would have been torn apart, I'm afraid. Now this brings us to our second and third phenomena: white holes and wormholes, things we know much less about and which are far more controversial. Basically, a white hole is the opposite of a black hole. Instead of matter being pulled into it, matter is pushed out of it. The idea is that if matter falls into a black hole, it comes out of a white hole on the other end, and matter in this case includes light, by the way. Light which enters a black hole exits via a white hole. This causes that white hole to appear as a bright white object. That's where it gets its name. Now, the actual tunnel through which the matter passes, from the black hole to the white hole, is called a wormhole, like a tunnel made by a worm. So you can see how the three phenomena are connected, right? Now, like I said, the idea of white holes and wormholes is still very uncertain. What I mean is, there's no empirical evidence of their existence. It's all only theoretical. However, if a white hole and a black hole could be linked somehow, then whatever falls into a black hole could, in theory at least, suddenly appear out of a white hole some other place in the universe. Yes, Christy, you have a question?
Yeah, I do.
Okay.
I once read a science fiction novel about people using wormholes to travel through time. Is that right? I mean, is it possible to travel through time using wormholes?
Good question, Christy. The simple answer is, we don't know. You're right, though. In science fiction, wormholes do allow people to travel across large amounts of space and time very quickly. If you want to understand how, just imagine an insect on a large piece of paper. It would take the insect a long time to walk across the paper, right? But if you folded the paper, the distance for the insect to cross would be much smaller, so it would cross the paper faster. Now, wormholes bend space in the same way that you fold a piece of paper. This means that just as the insect never crosses most of the paper, someone traveling through a wormhole never passes through the space between the entrance and the exit. He basically takes a shortcut, not just through space, what we call the third dimension, but also through time, what we call the fourth dimension. And the exit point, the white hole, may be somewhere far away, possibly in a different universe, linked to our own universe only via the wormhole. And if the exit to the wormhole is in the past, then you could travel back in time by going through. But, I repeat, this is more science fiction than reality, and many people deny the existence of wormholes. Yes?
But wait a minute. I thought wormholes had been proven mathematically.
True, it's been proven mathematically that they could exist, but that doesn't mean they actually exist in nature. And even if one day whiteholes and wormholes were shown to exist in reality, not just in theory, there'd still be at least two problems with traveling through them. For a start, scientists believe they wouldn't be stable. Therefore, even a small disturbance, like a person traveling through it, could cause the wormhole to collapse. In fact, some argue that in order to travel through a wormhole, the black hole, the entry hole, and the white hole, the exit hole, would have to be identical, and any small difference between them could destroy the wormhole. So that's problem number one. The second problem's this. Even if wormholes exist and are stable, chances are you'd be killed by the radiation inside them. So you see, although these are interesting concepts, right now it's difficult to know how real they are or how useful they might be to us. All right, that's all I want to talk about today. I've tried to give you a simple introduction to three mysterious phenomena that astronomers are still trying to understand. Let me just recap some of my main points. I've said that black holes have incredibly strong gravity. That gravitational force pulls everything near a black hole into the tiny center of the hole called the singularity. When objects, including light, get squeezed into the singularity, they're destroyed. However, I made a distinction between rotating and non-rotating black holes. In the case of rotating black holes, if the object crosses the event horizon, the area just on the edge of a black hole, it may avoid the singularity and exit from a white hole in another part of the universe. This might, in theory, make time travel possible. You'll remember that a white hole is the opposite of a black hole. Instead of sucking matter in, it forces matter out. And a wormhole is like a tunnel that connects the black hole and the white hole. To wrap it up, I'll just say once again that there is evidence that black holes exist, even if we're not clear about how they work. We're much less certain, though, that white holes and wormholes exist, and if they do, what value they might be to mankind. One more thing to consider is this. If time travel is possible, then shouldn't we now be meeting people from the future? Okay, that's it for today. Any questions?